Hello, my name is Alycia Burch, and today I'll be talking about altering the ratio of palmitic and stearic acids in supplemental fatty acid blends and how they impact production responses of mid-lactation dairy cattle. First, I want to talk about how this research is relevant to today's dairy industry, and that's due to the fact that today farmers are being paid on the yield of milk components, where the fat component is easier to manipulate both positively and negatively through nutrition. And thus, more milk fat and milk protein means more income for those producers. Fat supplements are included in the dairy cow diets to increase the energy density of the ration, but to also increase yield of milk and milk components. But the fatty acid profile of the fat supplement may affect production responses. In a recent study done in our lab by D'Souza, looking at the effects of palmitic, stearic, and oleic acids in post-peak cows, they found that fat supplements that had more C16 or palmitic acid increased energy output in milk, seen here on the left-hand side with this 80% palmitic acid treatment. But that C18-1 or oleic acid increased energy storage and body weight, as seen here in the right-hand graph, in red with this 45% palmitic, 35% oleic acid treatment. And this study showed that the fatty acid profile of the supplement is important to consider, as it can have differing effects on production responses. And another study done by D'Souza, looking at altering the ratio of palmitic to oleic acid across production levels. They observed that these low producing cows, around 45 kilograms, actually responded best to an 80% palmitic, 10% oleic treatment, seen here in green, whereas the high producing cows increased energy corrected milk on a 60% palmitic, 30% oleic treatment, seen here in blue. And a follow-up study done by Western found that when she was also altering the ratio of palmitic to oleic acids, found that as you increase preliminary milk yield, cows increase energy corrected milk on a 60% palmitic, 30% oleic treatment. Well, another thing to consider is that these lower producing cows actually responded best to the 80% palmitic, 10% oleic treatment, very similarly to the low producing cows in the D'Souza study. And then a follow-up study performed by myself, we wanted to make sure that that 60% palmitic, 30% oleic treatment that was having those production responses in those high producing cows was truly due to the oleic acid and not the 18 carbon fatty acids due to biohydrogenation in the rumen. And we did find that the higher producing cows respond best to that 60 palmitic, 30 oleic treatment. But something else that we found interesting was that these low producing cows, averaging close to 45 kilograms, actually responded best to a 60% palmitic, 30% stearic acid treatment. So it made us wonder and look back at previous effects of palmitic and stearic acids. So again, on the left-hand side, this is just my low-producing cows. But if we look at this other study performed by Western, where she used commercially available fat supplements, one being this SA, which is a high stearic acid supplement that had 33% palmitic and 53% stearic acid, and then a PA supplement that was 84% palmitic acid and 4% stearic. She had an increase in energy corrected milk with this higher palmitic acid treatment compared to this higher stearic acid treatment, which followed similarly to that D'Souza study, where again they had an increase in energy corrected milk on this higher palmitic acid treatment compared to the other treatments. And one of those other treatments was a 40% palmitic, 40% stearic acid treatment. Now, it's interesting to note that the low cows in my previous study had 30% stearic acid in their treatment. So we were wondering what could be the ideal ratio of palmitic to stearic acids that would maximize production responses for these cows that are averaging approximately 45 kilograms of milk per day. And that led to this current study, which was to determine the effects of altering the level of palmitic and stearic acids in supplemental blends on production responses of mid-lactation dairy cows. And we hypothesized that compared to stearic acid, the higher levels of palmitic acid would increase yields of milk and milk components. We used 24 multiparous cows in a 4x4 Latin square design, where these cows averaged 109 days in milk and approximately 47 kilograms of milk yield per day. We then had 4 treatments, first being control here in black, which was non-fatty acid supplemented. And then we had 3 fatty acid supplement treatments, with the first being high PA in orange, which is 80% palmitic, 10% stearic, mid PA in blue, which is 50% palmitic and 30% stearic, and then low PA in purple, which is 30% palmitic and 50% stearic. Now, these 3 fatty acid treatments had the fatty acid supplements brought in at 1.5% dry matter of the diet. We then had 4 21-day periods with 5 sampling days at the end of each period. Now, in order to get our desired ratios, we had to use 3 commercially available products, first being a C16 enriched prill, then a C18 enriched prill, and then calcium salt, to achieve our approximately 80-10, 50-30, and 30-50. One other thing I want to point out is that when we were making these blends, we designed all 3 blends to have approximately the same amount of oleic acid, that was roughly 10%. We've had a typical Midwestern diet of corn and alfalfa silages. And these diets were all similar, except for the fatty acid treatments got their corresponding fatty acid blends, and these blends replaced soybean hulls when compared to the control diet. Also, these 3 fatty acids had a higher total fatty acid percentage when compared to the control. We recorded feed intake daily and collected orts on day 17 through 21 of the period. We also collected blood and feces every 15 hours during those sampling periods, where we used INDF as a marker for total tract nutrient digestibility. Milk samples and milk yield were collected on days 17 through 21 of the period, and they were analyzed for components and fatty acid profile. Body weight was recorded 3 times a week, and then body condition scores taken on the last day of each period by 3 trained investigators. We used the PROC limits feature of SAS, considering the random effective cow, the fixed effective period, and the fixed effective treatment, along with the interaction of the 2. Main effects were significant at p less than or equal to 0.05 and tendencies at p less than or equal to 0.10. Interactions were significant at p less than or equal to 0.10 and tendencies at p less than or equal to 0.15. We also had 3 pre-planned contrasts: control versus fat. Fat in all caps refers to the average of the 3 fatty acid treatments, the linear decrease of palmitic acid, and the quadratic decrease of palmitic acid. Now to dive right into the results. First, I'd like to orient everybody to my graphs. I have treatment along the x-axis with control in black, the high PA in orange, which again was an 80-10, the mid PA in blue, which was a 50-30, and the low PA in purple, which again was a 30-50. We have our variable of interest on the y-axis, and my p-values are at the bottom of the screen, and any p-values that are bolded are significant. First, when looking at dry matter intake, we can see that there was no treatment effect, nor is there any significance between the contrasts. Next, looking at milk yield, we did have a treatment effect, but overall fat increased milk yield on average of 1 kilogram per day when compared to control. Looking at milk fat content and yield, on the left, looking at milk fat content, there was a treatment effect, but overall fat on average increased milk fat content by 0.11 percentage units when compared to control. We also observed a linear effect, which is due to the fact that as we decreased palmitic acid, we linearly decreased milk fat content by 0.09 percentage units. And milk fat yield followed a similar trend where we did have a treatment effect, but overall fat increased milk fat yield by 0.09 kilograms per day when compared to control. And again, we did observe a linear effect where as we decreased palmitic acid, we linearly decreased milk fat yield by 0.04 kilograms per day. Next, looking at milk protein content and yield, on the left-hand side, we have milk protein content. There was not a treatment effect, but overall fat on average decreased milk protein content by 0.07 percentage units when compared to control. But when we look at milk protein yield, there was no treatment effect and no significance of the contrast. Looking at 3.5% fat-corrected and energy-corrected milk, we have fat-corrected milk on the left-hand side. We do have a treatment effect, but again, overall fat did increase fat-corrected milk on average by 2.1 kilograms per day when compared to control. We also observed a tendency for a linear effect due to as we decrease palmitic acid, we linearly decreased fat-corrected milk by 0.80 kilograms per day. Energy-corrected milk on the right-hand side followed a very similar trend to the fat-corrected milk, where again we had a treatment effect, but overall fat increased energy-corrected milk by 1.7 kilograms per day when compared to control. And again, we had a tendency for a linear effect, and this was due to the fact that as we decreased palmitic acid, energy-corrected milk was linearly decreased by 0.70 kilograms per day. In summary, overall, the fat treatments increased production responses compared with the non-fatty acid supplemented control, as fat increased yields of milk, milk fat, 3.5% fat-corrected milk, and energy-corrected milk. Additionally, fat did not affect dry matter intake. Also, decreasing the level of the palmitic acid in the supplemental fatty acid blends decreased production responses, as we found that decreasing the palmitic acid linearly decreased milk fat yield. Additionally, decreasing the palmitic acid tended to linearly decrease both 3.5% fat-corrected milk and energy-corrected milk yields. Some implications from this study is that, again, the fatty acid profile of the fat supplement matters, as production responses can vary. In our study, we showed that higher levels of palmitic acid, when compared to stearic acid, increased production responses in cows averaging approximately 45 kilograms of milk per day. This is important for nutritionists and dairy producers to consider when adding fat supplements to the ration, as specific fatty acid profiles can be tailored to production levels to help maximize production responses and thus income for those producers. I'd like to thank the Locke Lab Group along with the MSU Dairy Farm staff. Thank you. I'll take any questions via email, or please feel free to come to the live session on Monday, April 19th and ask me any questions that you have. Thank you.